You've probably heard of colour spaces called srgb, Adobe RGB, maybe even ProPhoto RGB. But did you know that in Darktable the recommended working colour space is Linear Rec2020? In this video I'll try and explain what a colour space is, maybe in a very simple manner, but mainly what the word linear means in the name. And we'll see that this colour space enables me a better calculation of colours that would be possible in Adobe RGB or srgb. And to my knowledge, Darktable is the only raw processing software to this day that enables me to use this colour profile. Let's go. Let's start then with this first drawing of the spectrum of visible light, which goes from 380 nanometers to 750 nanometers, and those are the different wavelengths that the eye can detect and perceives as colours. Now in 1931, the International Commission on Lighting, which is the CIE in French, Commission Internationale de l'Éclairage. So in 1931 the CIE published a mathematical model of light. So how did they do that? Let's just do quickly, just show you the experiment they did. So they had someone here who was looking at an object, and this object was lit with a particular light source. And on the other side, so kind of in a split kind of way, ingenious device I suppose, they had the exact same object, but with it was lit by three different lights. One was red, so let's say around here, and one was green in the 500 nanometers, and one was blue here. One was blue, I think 435 I think at the time. I believe these particular wavelengths were chosen because they were actually easy to make. So these are monochromatic lights, so with just one unique wavelength for each. And here the operator could just change the brightness of each of these three lights. It couldn't change the colours, just the brightness. And the idea was to change the brightnesses of red, green and blue and try and perceptually to match the colour of the light he was seeing on here. So there's a light shining here with a particular colour, and trying to match the colours. And then what could they derive from that? Well, for each colour that was lighting the cube or the object on the left, they had three numbers. So let's say if in percentage between 0 and 100%, and otherwise we get just a real number between 0 and 1 for each. Okay, between 0 and 1 and between 0 and 1. And from these experiments, so multiple experiments, multiple people taking part, they derived this graph here which you have on the right. Now how does this work? For one particular wavelength, let's take a wavelength of 600, so we're in the oranges here. For 600 nanometers, so 600 nanometers, the operator would have put 0 blue, would have put, where are we here, about 0.7 or 0.8 green, and quite a lot of red, let's say 0.30, I don't know, where are we, 0.32. And so the conclusion is that the mathematical model, rather, is that for 600 nanometers of light corresponds three numbers. So 0.32, red was chosen first, R, green 0.08, sorry, 0.08 and 0. And here we have the first mathematical model with three in a 3D space of red, green and blue that matches the visible light. Except for, well, they did notice a problem. If you see here, the red goes underneath, it's negative. Now how can you get negative intensity light? Well, the answer is you can't. The problem was, you see, is that for certain wavelengths, just underneath the green primary, so it'd be around here in the cyans, there was no possible way to match up these three red, green and blue lights to match a cyan or any colours in this area. So what they did to solve that problem is they added on a red light source onto the original object to change the colour of this object, and then they could match it up with the red, green and light primaries. And then mathematically what happens is that if you're adding light here and you have light here, then to get the coordinates, the actual corresponding red light is you'd subtract how much red the user would input here minus how much red there was extra lighting up the cube or the object. And that is why some of the answers here are negative. So this makes what is called the srgb colour space, which is a colour space in 3 dimensions. So with 3 axes, R, G and red, green and blue in 3 dimensions, each colour being a coordinate in this 3-dimensional space. Now these negative numbers were a problem, so from one mathematical model they tried to derive another one, which is what is called the CIEXYZ, which is just a different view on the same thing. Now how does that work? Just quickly, if I do a quick example in 2 dimensions. So imagine you have 2 axes there, coordinate system 1, 2, 3, 4, and 1, 2, 3, let's say, and we have a point. Let's put point A here. What we'd say is that if you count 4 on the x-axis and 2 on the y-axis, then the coordinates of A are 4, 2. Mathematically, you can actually change the axes without changing the points. So you just change the coordinate system, and we could even change, let's say if we change like this, and we have now the x here and the new y that are there, then we might count again, and we might have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, and maybe we'd actually find that in the new system A would have coordinates 5, 5. Now the point A hasn't changed, so the colour space and all the results they found for the RGB model are exactly the same as in the new model. It's just the coordinates have changed, and that's what they did. Now there is an infinite number of ways to change the coordinate system. Don't forget, we're not in a 2D model, we are in a 3D model. So they actually tried to do this intelligently, and they decided that they didn't want any negative numbers, so they pushed the axes out of the way so there'd be no negative numbers. Quite a few constraints, I don't remember all of them, but that was one. And another one was that one of the axes would be orientated so that it would only represent the luminosity of the colour, and it wouldn't have any effect on the chromacity, which is kind of the what we imagine as the colour. So they tried to separate the luminosity from the actual colour itself, and so they came up with this model here, which is what we call the CIEXYZ colour space. CIEXYZ 1931 colour space, which is still used today. And on this graph, if you want to show the spectrum of visible light, then it actually makes a horseshoe shape. Well, that's what they found. It was a horseshoe shape in this new coordinate system, going from the blues, the ultraviolet into the blues, and into the reds, into the greens, sorry, oranges, reds, and then after that you can imagine the infrareds. So the colour space goes from, let's say, about 450 to 650 here. There's an imaginary line that's been drawn here, which is the magenta line, because once you have the locus of all the individual wavelengths, then you can actually mix those colours together, and from the spectrum of visible light you can actually derive all the colours that are visible to the human eye. And this is what we have here. So we now have a mathematical model of all colours visible to the human eye, with its coordinates, and that was important in industry at the time, to be able to have a norm for colours. So everyone knows that let's say at 0.4, 0.2 in this space, then it's this colour here, which is a big kind of reddish magenta, and that means that from one firm, one industry to another, we could actually have the same idea of what a colour is. So this is a mathematical model of colours. Now let's fast forward and let's get to computer spaces with when we're doing editing with photo software. So let's go here and take this picture here and insert it, and everything is done relative to this CIE 1931 XYZ diagram. So inside this now, for computers, to edit photos, video, anything you want, the model we use is a model with 3 primary colours. So let's start with srgb, and if we have in srgb, we can actually choose inside this XYZ space, we can choose a red primary, a green primary, and lower left a blue primary. And we know the coordinates of these in the XYZ space, so those colours are defined. And those colours now become the 3 primaries in the new colour space. So red would have coordinates 1, 0, 0, green would have 0, 1, 0, and blue would have 0, 0, 1. And if we mix those colours together, we can actually get any colour inside the triangle. That's why the lines are straight, because if you're mixing these colours with positive coordinates, and you're mixing those, you can go inside the triangle. So that is what's called the gamut of srgb. If you change the primaries, then you can actually calculate and display potentially more colours, and that's what happens if you just move the green along. You go to the Adobe RGB space, which is larger, and now green has changed, which just shows that in any computer model of a colour space, when you say green, it doesn't mean anything. It's just an arbitrary choice. So all colours are relative, if you like. This green is chosen. It's no better, it's no worse, it's just in a different place. But the colour space is bigger in gamut. There are more possible colours you can be calculated. Okay, so just a quick interruption to get a couple of things out of the way. Just to be honest, I am not a developer, I'm not an engineer, I'm just an amateur photographer, probably, like you. I did discover Darktable, the new scene-referred workflow, with the linear space, the Linear Space Rec2020. And Darktable 3, and now we're going up to 3.6, are a complete paradigm shift compared to what I was used to in Lightroom at least. So I needed to get my head around a lot of things and try and understand. So I'm supposing that it may be the same for you. We need to find the motivation to learn and to do things very differently, then maybe that motivation will find it by understanding why it's worth it. Because read on the internet, on the blogs, the video posts, that this scene referred workflow is better than the display referred workflow, and that I believe. Yes, I just needed to understand what it was all about, and this is what I'm doing in this video and the previous one I'm filming. Now I know there are probably loads of errors, omissions, errors, mistakes, ignorance, and that I admit to. But I still wanted to do these videos because I believe that for anyone who wants to move forwards, well, we have to start somewhere. We have to start with something that looks a little bit coherent, something that we can start learning with, and that might, or it will probably, help us to learn more, change the model we have in our head, make it evolve, and generally improve. So that is the motivation for these videos. Now I know also that I haven't talked about the difference between the workspace, which is XYZ, and XY and capital Y. I haven't talked about white points at all. The truth is that I'm not sure really what to say about them. What I want to do in this video is get to the end where I can actually show that in two different workspaces, one that is linear and one that is not, then there are visible differences when we try and mix colours, when we try and work with transparencies. So that's what I'm getting to. There we are, interruption finished, and let's move on. If we now go to the Rec2020 space, then all three primaries have changed. So the new red is here, the new green is here, and the new blue is nearly on the edge there. That's blue. So the gamut is larger. It's not the biggest gamut you can have. If you look at ProPhoto RGB, then you'll notice that the primaries are actually outside of the visible space of the colours that are visible to the human eye. The green is outside, and so is the blue. So that inside the triangle there are some areas that are outside the actual visible colours, which make what we call imaginary colours that don't correspond to anything in the physical world. But you can get larger. That is not, however, the end of the story. That is only the second step in the story. We need another step, because we have a problem after. Once these colours have been chosen, we have the problem of getting them onto the screen. And getting them onto the screen is actually not as direct as you'd think. What happens, you see, when you want to get something onto the screen? I'm going to make a little diagram. We're going to talk about just luminosity. Luminosity. For the colour I have in the colour space, its luminosity will go between 0, darkest black, and 100%, we'll call 1. Each colour has its own luminosity. And on the screen, we have here the screen, the luminosity of the screen. We have 0, which is the black pixel, and 1, which is the brightest pixel, the brightest white you can have on your screen. And we notice, I think probably you've heard of this already, but if you want to have, you've all heard maybe that 18% is middle grey, and this is because if you have a grey in this in your colour space which is at 18% luminosity, then it will actually appear on the screen to be a mid-grey. If you take the 0% to the 0.5 here of luminosity in the real colour, then it will actually appear to be very, very bright. So we do have a problem here, is that the darker colours actually appear brighter than what they really are. Black will appear black, white will appear to be white, so 1 goes to 1. And then there's actually a curve that needs to be applied to the colours. Let's see if that goes okay. That looks okay. Look, we have a curve that looks a little bit like this. It looks something like that, which is a function. This is called a transfer function. A transfer function. Now, I've heard that some people call it gamma, and I've already read that you should not call it a gamma. So anyway, it's a transfer function that will give the correct luminosity on the screen, so that the colours you're seeing actually appear at the right brightness. And you'll find this in srgb, You'll find this in Adobe RGB. You'll find it in ProPhoto RGB, most of the colour spaces. There is associated to the actual colour space itself, there's a transfer function. So it is a colour space is not just simply a triangle of gamut. There's also a transfer function that's associated to it. And that is a problem. That is a problem because if you're actually working in srgb and Adobe RGB, the calculations you're going to do on the pixels, on the colours you're actually seeing, are not correct because there's been a change in luminosity. So what happens, this is where the Rec2020 comes in. Because in Rec2020, what is called Linear Rec2020, so here we can actually go to, if we're working in Linear Rec2020, then there is no transfer function applied, or if there, yes, if you like, it's just a one-to-one function at 0.5 input gives 0.5 output, 0.18 input would give 0.18 output. So it's what's called linear. So this is a workspace. It is not a colour space that you can actually use on a screen because the brightnesses will be wrong. But if you want to calculate colours correctly, then you need to be in a linear workspace where things would happen as are expected. Because what would you expect? That when you're mixing a red with a green, you'd imagine that you get a yellow. And if you're mixing a blue with a green, you'd imagine that you get a cyan. And if you're mixing a blue with a red, you'd imagine if you're mixing the same amount of each colour each time, you'd imagine you get a magenta. And that is what's expected. And that is what you actually get in Linear Rec2020. And it might surprise you to hear that if you're in srgb, Adobe RGB or ProPhoto RGB, that is not what you get. And we'll see that just in a second. Just the last thing to say is that if you're in a Linear Rec2020 workspace, then you need to add an extra step to get your picture up on the screen, because at one point you do have to apply a transfer function to get the luminosity correct on the screen, but you want to do all your calculations in the workspace. So let's see what happens in a real life example. So here we are in a piece of software called Krita, which is designed for drawing. It's free, so you can download that if you want to try. And I've made two identical files with 3 circles using the primary colours red, green and blue. This file is in srgb and this one is in Linear Rec2020. Absolutely identical files. Let's start on this one. So with the 3 layers, I put the circles on 3 layers so I can move around the red, greens and blues independently. So for the moment the layers are in normal mode. If I want to start mixing the colours, we know that colours need to be added, so I'll put this into addition, and we have the mixing of colours between blue and red, which makes magenta, blue and green, which makes cyan. And if I put this one into the addition blending mode, there we are, should see we have between blue and green, we had cyan already, sorry, and red and green we have yellow, and where the 3 appear when we add the 3 primary colours we find white. So that is what's happening in srgb. Now what I'd like to do is to mix the colours together, not by adding them but by blurring them together, which might be something we'd see in photo software. So if I select just the layer here with the circles that have been merged into one, I can add a Gaussian blur. And I did this before. It's a Gaussian blur with a radius of 250 pixels. Let's get that blurred together. And this is something you've probably already seen before in Photoshop or Affinity. The blur between the colours makes some kind of dark dark shading between them, which is not what you'd expect really, because if you're blending red and blue, we'd expect to see magenta, and between the red and the green we should see some yellow, and the green and the blue we should see some cyan, and that is not happening. So let's have a look what happens if we're in Linear Rec 2020. So with the adding, let's try and move these together and then put them into the addition blending mode, just to see that when I'm adding them I have exactly the same thing whether I'm in srgb or whether I'm in Linear Rec 2020. What's interesting though is when I have the second layer that appears with the layer here with the circles I want to blur, and if I blur those with the same Gaussian blur, we should see something slightly different, which seems to be more in line with what I was expecting. So between the red and the blue I can clearly see some magenta, between the red and the green I clearly see yellow, and between the green and the blue I can clearly see cyan. If you want to see that again, let's go back to srgb. That's the blending with the dark colours, and that is the blending in Linear Rec 2020, and this blending is much closer to what I'd expect in a real physical world, and not this kind of darkening of colours. So that is important to remember, and that is the importance of using a colour space which is called linear. Just to show you, if I want to have a look at the other colour spaces, I could actually just have a look at the colour spaces available, and you can see that for srgb we have 3 primaries that have been chosen inside the XYZ colour space, and this is interesting. This is the transfer function for brightness, which is not a straight line. If you have a look at Adobe RGB, you'd see the same thing. The primary colours have moved, so the triangle is bigger, so we have a bigger gamut of possible colours, but the transfer function is the same. And you could have a look at most of these. ProPhoto RGB is the same. The primary colours change, but the transfer function isn't aligned. There are some, like Linear Rec 2020, where we have quite a large gamut of colours and this all-important line, and that is what makes our colours blend together much better. So how does all this affect me when I'm editing a photo? Well, in several ways. There's one I could show you. Let's say that if I make a new instance of colour balance, and I want to add contrast, let's say, or add some colour, but just to a part of the photo. So I'm going to make a drawn mask, and let's have a gradient. Let's say it doesn't really matter where it is, just to show what's happening. Let's make that gradient a bit smoother. And I hope you'll understand when you see the mask. So what's happening here is I have a mask which has been blurred, and the effect here in the solid part will be some extra saturation, let's say, or I don't know, whatever effect you want to sharpen, you want to blur, you want to just make a change, and then it'll blur, it'll gradually go down and down, and here in this bottom part of the photo there's no effect. So really what is happening is that in the part here where the mask is blurred, then there are colours that are mixing together. They're mixing together in exactly the way I just showed you on Krita. So in any place, in any file where you have masks with feathered edges, then it's very important to be in a linear workspace to get correct colours. In Krita, let's create 2 new files and do another experiment. So a new file in Rec 2020 with the linear transfer function. Let's create that, and let's get a nice red colour and make a red blob in the centre. And let's get a new layer, a new paint layer, and let's paint this layer with a bright primary colour, bright green. Now, what I'd like to have a look at is what happens when I lower the opacity of this layer down to 50% to mix the colours, which is really what an alpha channel is. An alpha channel is a layer that is not that doesn't have 100% opacity, so it will let some colours through from underneath. Therefore, there's a mixture of colours that's been made. So here I have paint layer number 2, which is green, underneath paint layer number 1, which is red. So here I have a mixture, an even mixture of red and green, which makes orange, and around it I have an even mixture of green and white, which makes a light green. So that looks fine. Let's do the same thing now with another colour space. Let's choose Adobe RGB, which is not linear. Create that, and let's do the exact same thing. So red 100%, big red blob, new layer, and let's get this one green and cover this in green and bring down the opacity to 50%. Oh, click first time, that's good. And now what we notice is that the mixture of 50% green and 50% red doesn't make an orange but makes a brown. And the green I have around it, which is supposed to be 50% white and 50% green, is actually much darker than the one that I have in Linear Rec2020. So this is another example of the differences between the two, and if I understand correctly why this linear workspace is better for developing photos, because the colours we get are more precise and more what you'd expect when you mix colours in a physical world. So there are. Well, this ends this video. I hope you enjoyed it. I hope you learned something. Don't forget that whatever I have said here today, take it with a pinch of salt. Go and read Wikipedia. Try and learn more about colour spaces, because as I said before, I am no specialist. These experiments have convinced me that there is a difference between the two, and I can understand why a linear workspace is said to be better, and that is as far as it goes for me. So there we are. Well, see you later and take care.